Hi, my name is Elizabeth Stanley, and my presentation is on the Wallace tree multiplier. The Wallace tree multiplier is a type of hardware implementation for multiplying two binary integers. It was developed by Chris Wallace in 1964 to be a very fast method of multiplication that uses fewer gates than the Booth method, which is also very fast. It is especially popular today because of the high demand of fast three-dimensional computer graphics, high-speed floating point processing, etc. Almost every digital signal processor today has dedicated multiplier units. Low-cost general-purpose microprocessors have them as well. The method first generates a set of bit-by-bit multiplications, where each bit in the first number is multiplied by each bit in the second, resulting in n-squared partial products. The partial products are assumed to have weights, which keeps track of which binary digit they correspond to in the product. Partial products with the same weights are combined in a series of reduction layers that use half-adders and full adders. Full adders are used as 3-input, 2-output combinational circuit that produces two sums from 3 inputs. Adding the final two sums together provides the final result. This type of multiplier is not much slower than addition, but requires far more gates. In this presentation, I will explain in detail how the Wallace tree multiplier works by going through the example of multiplying two 8-bit binary integers together. As I said in the last slide, the Wallace tree multiplier is a fast way to multiply two binary integers. And like any multiplier, the Wallace tree has 3 stages: partial products addition, and final addition. In the first stage, we calculate partial products. This works exactly like longhand multiplication. I have two numbers here, and they're going to be multiplied in this example, and they're boxed in. And we're going to do this by multiplying the least significant bit by this entire sequence up here. So, because the least significant bit is a 0, we get a row of zeros, which is shown down here. And then we go to the next least significant bit, which is a 1 in this case. Because it's a 1, it results in this entire sequence here. And we bring that down here and shift it over 1. Then we have two 1s next in the sequence. So because of that, we just bring the top sequence down here twice. Then we have two 0s, so we have 2 rows of zeros down here and shift it over each time. And then our last two bits are both 1s, so we just add this sequence down here twice. And then normally, in regular longhand multiplication, you would add up all the columns. But it's tricky to do that in binary, and that part's going to be taken care of in stage 2. So each of the partial products are shown in a blue square, and they're the result of a simple AND gate, because that's how it is in binary. And all of the products are done simultaneously because all the AND gates are done in parallel. This makes this stage really fast, because it's as fast as only one AND gate. However, this requires a lot of hardware. In this particular example, we would require 64 AND gates. The trick to the Wallace tree multiplier is in how the columns get added up. In stage 2, we add up the partial products. To add up the columns, we have to add the partial products up 3 rows at a time. To do this, we have to partition the rows up into sets of 3 rows. In this particular example, we have 2 sets of 3 rows and 1 set of 2 rows. We have to do it in 3 rows in particular because a full adder requires 3 inputs. And then the results of the addition for this step are shown down here. The green numbers means that they are just carried down directly from up here. For example, this 0 up here is all by itself, so it just needs to be brought down here. And then this 1 gets brought down as well, because while it's technically in the same column as these 3, in its own set, it's on its own. And these 2 rows are all green, because we're leaving them alone for now. We can't do anything with them because we don't have 3 rows. Next up is the yellow numbers. If a number is in yellow, that means that it's the output of a half adder. You need to use a half adder when you only have 2 bits or 2 inputs. In this particular example, 0 plus 1 is 1, so down here we have to put a 1 in the sum and a 0 for the carry out. Next up is the full adder stuff. The outputs of the full adder are shown in red. So 0 plus 1, that's 2. So you need to put for sum 0, and you need 1 for the carry out. Here, 0 plus 1 equals 1. We don't add in this guy because he was already taken care of. Since the result is 1, we put a 1 in the sum and a 0 for the carry out. Then we repeat the process again. We partition the rows into 2 sets of 3 rows this time, no leftovers, and we do the same thing again. 0 and 1 are by themselves, so they get carried down. 0 and 0 are in a half adder, so they're in yellow. 0 plus 0 is 0, so the sum is 0 and the carry out is 0. In the full adder, there are 3 1s. 1 plus 1 plus 1 is 3. So down here, we have to put 1 in the sum and 1 in the carry out. This stage takes a lot of hardware, as you can see, because there are a lot of adders and a lot of half adders involved. The gray boxes over here indicate that summation bits have been moved down to the carry out row. This is mainly for cosmetic purposes. Now we have to repeat the process again. We have 4 rows, so we just partition into 1 set of 3 rows and 1 set of 1 row, which is the leftovers. 0, 1, and 0 get carried down. 1 and 0 are in the half adder, so the sum is 1 and the carry out is 0. And you do the same here. 1 plus 1 is 2, 0 and 1, etc. And you carry down this row because it's by itself. And each step takes as long as a full adder because that is the slowest part. A full adder is more involved than a half adder, and a half adder is more involved than just carrying down. Carrying down literally takes no time, so. And all the adders are done in parallel, which adds to the speed. We have to repeat the process one last time. We don't need to partition the rows this time because there are only 3 rows left. These 4 guys are all on their own, so we carry them down. Then here we need 3 half adders, as opposed to the 2 in the last step, and 7 full adders. In this example, stage 2 has had 4 steps and 4 full adder delays. And, as seen here, the 5 least significant bits have already been calculated, which saves time in the next stage. In stage 3, we have the final addition. The final result is calculated by adding the final 2 rows together, since there are only 2 numbers left. 5 least significant bits are already calculated, so they do not need to be added. They just get carried down. So the rest of the bits, they all have to go into 1 adder, which involves a lot of delays. The output is shown in the purple numbers. The savings from already having 5 bits offsets the delay from doing stage 2. The result is that the Wallace tree multiplication takes about the same amount of time as a 2n-bit ripple carry adder. In this particular example, that would be a 16-bit ripple carry adder. For the time delays, stage 1's time is negligible. It takes up the amount of time that one AND gate takes to AND 2 bits together. Even though in this particular example, there are 64 AND gates, they're all in parallel. So it only takes up the time of one AND gate. For stage 2's total time, it takes up 4 times the full adder delay. If there were more bits in each of the numbers being multiplied, that 4 might be a 5 or a 6 or an 8. Or if there's less bits, it would be a 2 or a 3. It all depends on the size of the numbers you're multiplying. Stage 3's total time is the greatest, because there can be delays as the carries are propagated in the final addition. The time taken for stage 2 is saved by having fewer delays in stage 3. In summary, the Wallace tree multiplier is a type of hardware implementation for multiplying together 2 binary numbers. It is especially popular today because it is really fast and there is high demand for fast 3-dimensional computer graphics and high-speed floating point processing. Low-cost general-purpose microprocessors have them, and almost every digital signal processor today has dedicated multiplier units. This type of multiplier is not much slower than addition, but requires a lot more gates. In this presentation, I explained in detail through an example how the Wallace tree multiplier works.